hao, welcome und hallo. So it's a great pleasure to be here. So I was a little bit confused because we are in front of the time and I wanted that you are not going to sleep during my presentation. So that's why I had it a little bit earlier. So now I recognize we are on time, so I have 45 minutes now, if I can see this. Okay, I can take a little bit more time. Okay, so Thomas, I'm a 3T guy, and I will tell you why. So here I'm representing Solar Lab AIKO. What is Solar Lab AIKO? Solar Lab is the first European research hub founded of one of the big Chinese manufacturers in Europe. So we founded this in Freiburg in Germany, next to the Fraunhofer ISE. And Solar Lab is part of the global R&D infrastructure of AIKO. So AIKO is a very technology-driven company. The DNA is in our blood. And the initial focus was to support the PERC customers we had in 2020. Because in 2020, AIKO was a pure PERC manufacturer, no ABC at that time. Another big topic was what Peter also mentioned today. We wanted really to prepare a production in Europe. So we had a lot of talks with different governments, with local guys to do this in Europe, but the business case is really hard to find. So it's not a free market, this is always subsidized markets. And if you have to deal with European politicians for subsidies, it's really a nightmare. So I gave up a little bit. I'm very happy that I have some colleagues which are still fighting and I hope that they will succeed. So right now at Solar Lab, we are focusing on perovskite and we are doing some module tests for ABC because a lot of people want to have independent tests. And yeah, you said, what is the future? So we all know these charts from NREL, so where you have the world record cell efficiencies. And the limit of the silicon single junction cells are, let's say, theoretically at 29.5 or something. And at our labs, we have now 27.5. So we are in the area of, let's say, 28%. So this means the modules now we have at 25%, maybe next year at 26%, but then there will be a limit. And to overcome this limit, there are some possibilities, and one possibility is a tandem cell. So tandem silicon, in our case, silicon and perovskites, is our solution, which we are testing. I'm often asked, when will it come? And this is a really good question. You can bet there are a lot of efforts here, especially in China. I saw some really nice pilot lines from suppliers. And it's hard to say, maybe within the next 5 years, maybe in 3 years we will see something. Let's see. So there are, let's say, for tandem cell configurations, 2, 4, and 3 terminal applications. 4 terminal is more or less that you put another solar cell on top of or another solar module on top of the solar module, which can have some advantages, but this is not our approach. 2 terminal would be if you have a PERC cell, and 3 terminal is what we are favorizing from Solar Lab, and I will explain you why. So there are some properties. 2 terminal means current matching, and 3 terminal means voltage matching. And this can be a big advantage in energy harvesting because it's not sensitive to spectral conditions. And therefore, we think that the energy harvest with 3 terminal can be much bigger. So can be used for monofacial and bifacial. For 2 terminal, it's quite easy. These are the standard cells. And all these discussions for 3 terminal, I would also say yes, because also as you have seen with the ABC cells or modules, we also can achieve 80% bifaciality. And the cost effectiveness is something Chairman Chen also said in the morning. We believe that we can have the same cost structure as the standard cells. So with proper technology, especially copper printing and other things, or copper plating, you have this cost structure which is the same like TOPCon. So this is a well-known tandem device. A lot of these technologies are also in the TOPCon devices, and so you have to add some some new processes. In AIKO, let's say, we compete a little bit with technology. My Chinese colleagues here in EU and we from Solar Lab, we compete in technology. So, but we are always exchanging our information, so we are not competing by persons. And in Solar Lab, we are using, or we are following a complete wet approach, but I will talk about this later on. So one potential of these tandems is a cost saving. And you can save a lot in metallization because you increase the voltage a lot and you decrease the current. And for this decreased current, you have low resistance losses and you can have less grids or less grid area. And this is a big advantage. We calculated in a Bayesian simulation or optimization how less metallization grid you can have. Bayesian, by the way, is the name of the ship which sank, but this is a side story. I don't know if you remember. And for sure, if you make the grid smaller, you will increase your electrical losses, but you decrease your optical losses. And there you have a trade-off. This yellow dots with 30% is the optimum. And there you see that larger finger spacing with 2.5 millimeter and a bigger length is preferable. And this means you can save 50% of the metallization costs. What I said in the beginning is that there is a benefit in the energy yield, and you can see this here. As two-terminal approach needs current adjustment, and you have bifacial or monofacial approaches, then we simulated for two terminals with different band gaps for the perovskites. And the red line is, let's say, the current attraction. And there you can see in the bifacial, you lose a lot. Even if you have a much higher J, P current there, you lose a lot by this current junction. And with three-terminal, you don't have this. So that's why we believe a three-terminal can have a much better energy harvest. So we calculated this for different areas. So the more light, the better it is for three terminals. In Freiburg, we can win 2.2%. And here in Zhuhai, we can even achieve a better 6% energy harvest. One thing which is always discussed is stability. Maybe this is the biggest task in all these perovskite stuff, and this is also the question when it's commercially available. So now with silicon, we are talking about products with a lifetime of 30 years, and this is at the moment not in the horizon with these perovskite. So if you want to have a product which is maybe not as stable as silicon, you maybe can live with a little bit more instability, and this is something we calculated here. So it's a trade-off between efficiency and the reliability or stability of the product. And you can see the white line, there is zero, so there is no benefit. This means there is a trade-off of the higher efficiency and the lower stability. And if you have a much higher efficiency, you can live with a lower stability. For sure, the stability can't be too low. And this means, as an example, for a 27% module, the rate of stability must be less than 1.5% relatively. So these are things which we are dealing with in Solar Lab, and I show now what we are doing in Solar Lab. In the meantime, I want to congratulate my colleagues here in EU. They achieved the maximum laboratory tandem cell efficiency of 34.76. Kaifu, I hope this value is still correct. It's a very low hysteresis which they measured there, and it's very stable. So at Solar Lab, we're doing metrology development because three-terminal is not so easy to measure. So we do some aging tests, and what is our focus? We only want to use upscalable processes. So this is our timeline. We started in 2024. Now we did also the stability testing equipment, and now just recently we did the first three-terminal cells. So for the metrology development, we used equipment from the well-known company DIY, do it yourself. So we did this by ourselves. We did some contacting chucks. We do some measuring units, and then for the measuring, you contact two contacts with a certain voltage, and then you have one IV curve on this certain voltage, and then you have at least 10, 20, 30 measurements per cell, and this gives you the maximum power point. And it looks like this at the end, so it's more or less a three-dimensional graph where you can have the voltage of the channel A, the voltage of the channel B, and we developed our own software for this, and you see here the efficiency is then in the range of a little bit more than 20%. We use, as an upscaling process, slot die coating at the moment. Printing technology has the potential to be the cheapest one. It's also a bet in the future because it's also difficult to stabilize this. Maybe a full dry process can be also achieve better results. There are hybrid approaches. We at the moment are focusing on this complete wet process. And there are some papers which are shown 31.2% on blade coating. And blade coating more or less is nothing different from slot die coating. So the printing process, let's say, has to be optimized. That is something we are doing at the moment. So here you can see how the optimization process looks like. This is a macroscopic view. So on the left corner, you see our first approaches. So this looked very horrible. And over the weeks, we achieved a very nice ultra-black homogeneous film by adjusting a lot of these parameters. This is the microscopic view of the same, and here we are doing R&D now for, let's say, three months now on this slot die coating, and that's a very nice result in these 3 months. As I mentioned, stability is quite important, and therefore we did some assessments, and we did for the different stress factors. And therefore, we also thought about how you can avoid it. Yeah? So the big, very good sealant is extremely important, and we are working together with some commercial companies in Germany who are delivering new materials to us. These are very complicated chemical names which I can't pronounce, so I only use abbreviations here. We did a lot of tests with also the same company, DIY, which we produced. So it's light and electric stress. So we try to measure a lot of these small samples, these 1 square centimeter samples. Every cell was measured independently by MPP tracking in this chamber. And we got some really nice results. We got these sealants, which you see here. We took the standard one in the very beginning, and then we got these new ones from this German company. And you see that the green light, the passivation here, and the one sun illumination was quite good. So this is something which we figured out. If you want to talk about stability, these sealant materials are extremely important. There are materials which have, let's say, traps for oxygen, for moisture inside, and therefore maybe this can solve the stability issue in the future. So stability under light and electric bias, you can see the examples here. So down you see the temperature, and you see the normalized PCE. And for our approaches with these laboratory cells, this looks good in the meantime. So this means there is no blocking point or no hurdle which can't be overcome in the future. So stability under humidity and heat is also tested. This new material is called APAO, and this stands for I don't know what exactly, but this is for us, it's very highly transparent. It has a very low melting point, and it's extremely chemical stable. So we think it's very, very highly promising for tandem application, and it's commercial available right now, and not in a ton, but in some kilogram. this brings me to the end, and therefore I would like to summarize. So why we believe this 3T perovskite silicon tandem is a right approach, as Thomas asked in the very beginning. So if you compare to two terminal, it has a much higher energy harvest. It's not this two device thing which maybe Gianluca would be in favor of. I don't know if you're still in favor of. We can discuss later on. So what we did is we developed a lot of equipment by our own, this DIY stuff, which helps us a lot now in the next steps, and hopefully next year we can present nice results, hopefully to crack the 30%. The slot die coating is a little bit a miracle thing. You have to work in the glove box, and it's quite complicated to really adjust it well. So that is really laboratory work, as you did in your PhD. We are now starting bigger cells because we want to see from the very beginning that we can do it on bigger areas. We don't want to go for spin coating and square centimeter cells. So our goal is really to reach something which in principle can go to production, and we are production-driven people. So stability enhancement, this for sure is the biggest issue, and therefore the industry has to help us. This is nothing you can solve by yourself as a cell manufacturer or module manufacturer. But also in this industry, there are a lot of progress be done. And this APOA films, for instance, they helped us a lot, and maybe there are further inventions in this industry. So altogether, we can hopefully come to a very bright future. That brings me to the end. I say thank you, and hope to see you later on.